Welcome to Read My Hips. For the older generations, we sneaked T9 into the title of our presentation. But what can I say? A joke which is not understood may not be a good joke. Everyone reading our text, including the reviewers, was sure that this is a mistake. The Gore organization even changed our title several times as they believed something would be wrong about our title. We can assure you, everything about our misspelled title is right. Our talk is about the failure of AI transcriptions. We will explain to you why even artificial intelligence may need some human support from time to time.
Hi, my name is André Lang from Insius. Together with my colleague Stefan Müller, I'm responsible for the idea of the correction algorithm, development, and evaluation.
Hi, I'm Holger Lütters from HTW Berlin. In this project, I was responsible for the speech questionnaire programming and the panel integration. Thanks to our co-author Malte Frexer and the panel sponsor Gapfish, we were able to do this slightly deviant research project.
I am the avatar of Malte Frexer from Gapfish. We are the proud panel sponsor of this important research approach. Hope you enjoy this presentation. We will all be available in person for your questions right after the presentation.
Speech is about to become a standard in digital research interviewing. The process of integrating speech questions in a mixed-mode survey is possible with the existing market research infrastructure using standard panels. The text-to-speech part consists of an AI reading out loud text, like I do here. The speech-to-text part is the interesting part for interview research, where speech is transformed into written text.
When we first started using automated transcriptions in the field of online research using spoken voice answers, we discovered that in a lot of cases the software does not understand human voices the way it should. We got in touch with crazy transcriptions, not really understanding the initial words that may have been used. When someone said, "read my lips," the tools understood, "read my hips," and this is where our title comes from. So before going into text mining analysis, we need to make sure that the transcriptions are always accurate. Different transcription procedures and algorithms produce deviant results. Some of the problems are well known. First, the recording quality is determining the quality of the transcript. Bad technology settings like bad microphones or strong background noises are responsible for incorrect transcriptions. The second biggest influence is the respondent him or herself. The way people pronounce things has an impact on the transcription results. As the AI tools today only support a selection of languages and hardly any country-specific accents, this is a permanent issue. As researchers, our influence on the text setting and the personal pronunciation skills is more than limited. This is why we need to focus on the third category to work on some of the linguistic challenges like context identification, unknown words, etc. In an empirical approach, we tested different settings of brands as unknown words to artificial intelligence. The especially selected brands, which are difficult to pronounce for the average consumer, may cause a challenge to those who need to read out loud those brands. We then asked respondents in the survey to read out loud those fancy product names from Haribo packages. We asked them to read out loud car brands, telco brands, consulting brands, very difficult pharmaceutical brands, and even market research brands. Can you imagine how difficult some of the brands are to be pronounced when you are not working for one of those companies? The empirical approach with more than 2,000 contexts in the Gapfish panel helps to test the new algorithms and parameters developed by Insius. Andre is now going to explain this idea of the creation of a goal set to support voice transcriptions for the future of brand research using voice.
Thank you, Holger. The goal set we created is a reference solution which is used to test the different algorithms. We took the partially faulty transcriptions and gave them to a human coder who tried to find the correct list of matches being within. The baseline that our algorithm will be compared to is the exact match of each of the options in the transcript text. To find ways to improve speech transcription, we first need to understand how transcription works in general. At the start, we have some audio recording. This is just a WAV file, which you see here on the left. So it's the waveform directly taken from the microphone. Now, the first step is to apply an acoustic model. It maps parts of the waveform to distinct sounds, and these sounds are called phonemes. You find some of the phonemes commonly used in English in the table in the middle. It's very important to understand that these sounds are not directly mapped to a certain spelling. For example, you see the sound used in up and in cut, which is also present in the word money. So if written down, this phoneme could be spelled as an U, an O, or even something completely different. We have a huge number of such phonemes, and some are shared across languages. Okay, we now have a list of phonemes. The second step is to map the list of phonemes to possible transcriptions using a linguistic model, which is usually based on hidden Markov models. I'm not going to explain this in detail, so just remember that the linguistic model tries to create a transcription which will best match the phoneme list. As we now understand how the audio transcription works, let's get to the problems when using services like Google Text-to-Speech, especially if we are in a questionnaire situation. Although these algorithms are very advanced and giving really good results in some situations, they are optimized for certain use cases, like entering an address to get driving directions or running a Google query. The service itself does not know which language we are talking in advance, and even more important, it doesn't know the context. There is some automatic adaptation, but it is way unpredictable. So if you just say kangoo, this would usually be detected as kangaroo, as the context of talking about a car model is missing. However, if you instead say Pajero, kangaroo, or something else about cars, it is detected correctly, because now there is sufficient information to derive the context. We have seen this all or nothing situation several times when creating our goal set. Another problem is out of vocabulary, which means that you have a word, usually a brand or a product name, that is either completely unknown or sounds similar to a very common word. For example, we found that the institute name Respondi was almost always detected as Rispondi, so with an I, not an E, because that is the Italian word for answers. To sum up, speech transcription is a great thing, but it's a black box approach with some issues which we need to address. Okay, so what can we do to improve the results? Well, we said it's a black box, so from the raw audio to the transcription there is almost nothing we can do, because we have no other choice than to use the voice transcription service as it is. But maybe we can do something with the transcription. Let's have a look at the transcription output below. Do you have an idea what was actually said? I'm going to make it a bit easier. We asked for research institutes and services. Still no guess? Okay. Among the list of choices was Gapfish, Incius, Kanta, Pangea Labs, QuestFox and LiveLoop. So this is easy now. Why? Because you knew the context and the list of words in their pronunciation, so you have been searching for similar sounding parts in the transcription. So this is our way, going back to the phonemes to find a better matching and using our additional knowledge. To work with phonemes, we first need some converter to get phonemes for a transcription. Luckily, finding similar sounding text is a task that has been addressed long ago. The first method, SoundX, was used as early as in the US Census of 1920. The goal was to find similar sounding names to avoid double counting, and it used a set of replacement rules to create a fixed length 4-character encoding of the input. You see an example of the encoding for general online research below. Later on, a lot of work in this field was done in Germany. The first adaptation of SoundX for German was the Kölner Phonetik in 1969. It took care of German umlauts and pronunciation, but still wasn't perfect. Jürgen Michael published a new method, Phonet2, in 1999, implementing about 600 replacement rules, catching many special cases, and working on German and English alike. Phonet2 is also very easy to understand because you can just read out the phonetic code and get an idea how it works. Okay, so now we have phonetic codes for random input texts. But we still need a way to compare them and measure how similar they are. An easy but comprehensive way is the Levenstein distance. The Levenstein distance measures how many one-character insert, delete and replacement operations are needed to get from word 1 to word 2. Let's have an example. You see the Phonet2 phonetic code for Dacia Duster. To get to the phonetic code of das da, you need to insert one space, which is represented by a hyphen, and replace the U with an A. So it's 2 operations and the Levenstein added distance is 2. We now have all the tools needed, so here is the idea how to do the repair. Given the list of possible answers, or words or phrases that could be present in the answer, check if there is something sounding similar. If found, count that match and repair the original text if needed. So let's see this in action. We have a list of energy providers that is shown to the respondent, so a closed list of possible answers. We call this one the vocabulary. In the second line you see the phonetic code and below the transcript to be repaired. In the first step we detect the exact and so-called literal matches, and we exclude the according phonetic codes from further detection. Second, we match the remaining codes printed in bold to the vocabulary codes. We find Vattenfall and NBW as similar phonetic codes, and in the third step, replace these words in the original text, effectively repairing the transcript. Please note that even though Vattenfall was fragmented to hatten and voll in the transcription, the correction was still found successfully. To evaluate the effectiveness of this repair, we applied the different phonetic algorithms to the goal set transcripts and compared the results with the manual coded truth. The result is that the accuracy boosted from 80% for baseline, which was literal matches, to 91% with the Phonet2 algorithm. It worked equally well on German and English. So, to sum up, this method can be used to automatically reduce false classifications by about 50% if the list of options is known. What remains left is to apply this algorithm to the more difficult scenario of open-ends, where the text length is much longer, increasing the risk of false positive matches. For everyone who would like to know more about this method and try out the examples shown, please visit voicefix.insys.com. We have set up a small test lab site there where you can test the different algorithms, play around with the different settings, and also try to repair your own transcripts. Thank you for attending this session.